Well, I hope everybody had a great May the 4th be with you yesterday. And maybe some of you were able to watch the final episode of the Clone Wars that came out. I did, and I must admit I got some chills at the end of the episode. I got a new Lego to put together, so celebrated in style. And now, of course, today's Cinco de Mayo, so I had tacos for dinner. Hope you guys are doing all right, and just wanted to give you some new notes here on what's called a series. So let me know if you had any questions on the sequence piece of things, and then we're going to move on here today to a series. So a series, okay, is just the sum of the terms of a sequence. So when we have a sequence and we decide to add it up, then that is known as a series. Okay, so if I were to write a sequence like 2, 4, 6, 8, 10, really creative there, right? So that's a sequence. But if I write 2 plus 4 plus 6 plus 8 plus 10, right, that is a series. So a series is when you add up the terms of a sequence. Okay? There are two types of series. There are finite series and there are also infinite series. So we're going to mainly look at finite series. They have a first term and a last term, but we can also have infinite series, which means, they go on forever. And we are going to focus on two types of series, both arithmetic and geometric. So that's what you would probably guess, right? If it's an arithmetic sequence and I'm adding it up, that's an arithmetic series. If it's a geometric sequence that I'm adding up, that's a geometric series, okay? So we want to try to look at a couple of, here, let's just take a look here. So it says, can you find the sum of the finite series, right? So if we look here at this series, is this arithmetic, geometric, neither? Okay. And so if I look at it, sure enough, right, each time I am adding 3. Right? So this is indeed arithmetic. And if I look down here, this one is also adding 3 each time, right? So this one is also arithmetic. So they're both arithmetic. Now you can see where that first one, it would certainly not be hard to just get out your calculator and add up 6 plus 9 plus 12 plus 15 plus 18, get an answer, done. But if you look at the second example, right, do we really want to add up all of these terms, typing them into our calculator? And I believe the answer is no. So let's see if we can develop a formula. So I actually tell you a little story here about a mathematician named Gauss. Now this could just be mathematical legend, but it is said that Gauss, when he was in first grade, overheard his father. I'm sorry, that was a different story of Gauss. I guess started to get my stories confused. Gauss was in first grade, and his teacher, as a punishment to the class, said that they needed to add up all the numbers from 1 to 100, right? So she was upset with the class and said, okay, add up all the numbers from 1 to 100. And so she thought that'll keep him busy for a while. And Gauss raised his hand within about 20, 30 seconds and had the answer. So the question is, how did he do it? Was he just so mathematically gifted that he could add all those numbers in his head? But the legend goes that he found a quick pattern. So if you're adding up the numbers from 1 to 100, that is arithmetic, right? That's an arithmetic series. You're going up, the constant difference there is just 1. So it's said that what Gauss did was he said, well, if I write that out from 1 to 100, if I turn that around and add the series up again, but this time I count down. And so then if I vertically add that, 100 plus 1 is 101. And 2 plus 99 is 101. And 98 plus 3 is 101. And if I get all the way down here, then obviously those are going to be the same. So we said, okay, so when I add that up, I get 101. And since there were 100 terms, I get 101 times 100. Right? So 101 happened 100 times. So that would be 10,100. Right? I feel like I'm writing binary here. So that would be 10,100. But he said, but that was adding the sequence up twice. Right? So I'm going to divide by 2 because I just added it up twice. And so that would be 5,050. So the sum is of 1 to 100 is 5,050. Well, it actually turns out that if you have an arithmetic sequence that you're adding up, and so an arithmetic series, that what it turns out, if you look at the pattern here, and so rather than proving it, we'll just kind of base it off this pattern. I would have made us prove it had we been in class, but we'll just kind of go off the pattern here. So if we look at it, the idea is, well, we had n terms, right? Because if we're adding from 1 to 100, there were 100 terms. So if I wanted to add up 10 terms, there would be n of them. And the key is that when we look at the 1 and the 100, those are the first and the last terms of the series. So if I add up the first and the last terms of the series and multiply by the number of terms and then divide by 2, that will add up for me all of the terms of an arithmetic series. So if I come back up here, right, and I wanted to know what the sum, I'll do example 2 here, because that's the one we certainly probably would want to do with without having to just do them all by hand. So we want to add all those terms up. You say, okay, well, I start at 14, so the sum would be, well, we don't know how many terms that is. Oh, well, we can figure that out. Aha! Because we know that since this is, oh my, what just happened? We know that because this is arithmetic, there's my formula down there, the nth term is given by the first term plus n minus 1 times the difference. So basically I need to figure out which term is 116. So 116 is the first term 14 plus n minus 1 times 3, right? So if I solve this for n, then I am going to know how many terms I've got. Okay? So solving that for n, so if I subtract the 14 over, then I'm going to have 112 equals n minus 1 times 3. So if I divide, right, by 3, okay, so 112 divided by 3 is, wait a second, something's wrong. That would be because this is 113. Wow. No, I was right. 112. What did I do wrong here? That can't be right. Something's off. Hang on. You're probably yelling at the screen here. Oh, yeah, that would be because it's 102, isn't it? Yep, that would help. 102. Okay, we'll say because it's 11 o'clock at night. So 102, right? So 102 divided by 3 is 34. That's better. So n is 35. Okay. So we're actually summing up then the first 35 terms. So it's going to be 35. The first term was 14. The last term was 116 divided by 2. So 14 plus 116, right? 130. 130 times 35 is 4550 divided by 2. 2,275 then is the sum of the first 35 terms of that sequence, or that series. So there's your formula. Some books write the n over 2 like that, so they'll write it n divided by 2 times the first term plus the nth term. I tend to write it n a1 plus an all over 2. It really doesn't matter. You'll actually see it written one other way, where instead of a sub n, we'll actually plug in the formula for a sub n, right? So if a sub n, that's my formula, right, from 2 days ago. So I have 2a1s plus n minus 1 times d over 2. So that's another version of it. Okay. So they're all the same formula. I tend to just always use this one or this one. This one down here, to me, you don't really need, because as long as you know what the formula for the nth term is, you could always just find it that way. So, all right, so let's take a look at a couple of examples here, a little bit more. So, is it necessary to know the common difference when using the formula to find the value of a finite arithmetic series? Explain. So the answer, sometimes. Right? The common difference is necessary to find the number of terms or to find the nth term. But if the number of terms and the nth term are given, then you actually don't need it, right? So what's interesting, right, when you look at this formula, it's based off the first term, the last term, and then the number of terms. So nowhere in here, right, do you need the difference. Now, sometimes you might need it to figure out an or a sub n or n, but technically if you had the first term and the last term and the number of terms, you don't actually need to know what the difference is. Okay? So what is the sum of the even integers from 2 to 100? Right? So 2 plus 4 plus 6 plus ... all the way up to 100, right? What's the sum of that? Okay, well, how many is that? So from 2 to 100, that's going to be 50 terms, right? Because it's only the even numbers. So it's going to be 50 terms. The first term is 2. The last term is 100 divided by 2. Right? So plug that in to your calculator or do some mental math, right? Which I'm obviously bad at tonight. So 102 times 25, when you divide by 2 there, would be 2,550, right? So the sum of the first 50 even numbers, even integers, is 2,550. Way easier than actually punching in 2 plus 4 plus 6 plus yada, yada, yada. So what is the sum of a finite arithmetic series 4 plus 9 plus 14? So our difference here is 5, right? So it's arithmetic. So here's another one of these where we don't yet know what n is, right? So this is where we have to figure out how many terms are in this series. So we know 99 is the term. We want to know how far out 99 is. So the first term was 4. And we know that the difference is 5. So this is going to be 95 n minus 1 times 5. So when I divide by 5, right, so and 95 divided by 5 is going to be 19, right? So n is 20. So we know that we're adding up the first 20 terms of this series. And one thing too, when you're doing this, if this again goes back to if n had not come out to be an integer, right, or a whole number, a positive integer or a whole number, then we would know that we got a mistake here, that either 99 is not actually a term in the series, or we made an algebra mistake, right? So that's how a couple minutes ago I realized, I did something stupid here with my arithmetic, because I knew that wasn't coming out to be a positive integer. So this time, n equals 20 is, so I've got 20 terms multiplied by the first term plus the last term all over 2. Right? So 4 plus 99 is 103, and 20 divided by 2 would be 10. So 10 times 103, 1030. Right? So there we go. All right, so easy as that. All right. let's see. So let's take a look. Yes. So the last thing is that this goes back to earlier in the year when we learned sigma notation, that sometimes we write we can write a series using summation notation, right? So it's going back to what does this notation mean, right? So when we've got our big sigma symbol there, remember that means that we plug the bottom number in first. So 1 would get plugged in here, right? -2 times 1 is -2, plus 1 would be -1. Then I would plug in 2, right? So I plug 1 in, then I plug in 2. 2 times -2 is -4, plus 1, -3. So notice that this time I'm actually adding on a -3, right? So I'm adding -3. So I could say -3. Then when I plug in 3, right? So n is 3, I'd get -6 plus 1. So I'm adding on -5, and so on. Okay? So when I do that, I always suggest, just get a couple of terms to make sure you understand what's going on. But this one right here is going to be arithmetic. Okay? And the reason that this one's going to be arithmetic is because if you look, right, that is linear. So the fact that that was linear told you, without actually having to generate some terms, that it is going to be arithmetic. But if you weren't sure, you could always do a few terms just to make sure. And then you can look at it and say, okay, do I have a constant difference? Yes, I'm going down by -2, right? So d is -2, which notice was the slope, right? Okay, so if that is true, then this is a case where I can add up the terms, right? So how many terms do I have? Well, that's what that top number is telling us, right? It's saying stop at 27. So I'm adding up 27 terms. So 27 divided by 2. I'll write it this way this time. So 27 divided by 2 times the first term was -1. Plus, well, what's the last term? Well, the last term is what we get when we plug in 27, right? So -2 times 27 plus 1. So that would be -54, right? Plus 1, so -53. All right. So when we add this one up, so we're going to have -54, right? Times, so divided by 2, and then times 27, so -729. So notice that this time our series actually added up to a negative value, okay? And that's fine, right? Because in this case, as I proceeded through the series, right, I was going down by 2, so I was adding up negative numbers, and so I actually added up to a negative value, okay? Looking at letter B, I want to show you something though here. Notice that this time that n squared plus 5 is not linear, right? So that is not linear. So it is not arithmetic. So then you might say, oh, well, is it geometric? Well, if I do this one, and again, this is where, if you're not sure, right, just plug in a couple of values. So if I plug 1 in, 1 squared is 1, right, plus 5 is 6. When I plug 2 in, 2 squared is 4, plus 5 is 9. Plug 3 in, 9 plus 5 is 14. So notice that this time it was going up by 3, then it went up by 5, right? So then if I plug 4 in, I get 21. So then it went up by 7. So this is not arithmetic, and it is not geometric. And so if it's neither geometric or arithmetic, then we're just going to have to add it up by hand, which, if you notice, there's only 5 terms anyway. So when I plug 5 in, I get 30. And so I can quite literally on this one say, oh, well, that is not arithmetic or geometric. So what is 6 plus 9 plus 14 plus 21 plus 30 is 80, right? So the sum of that one is 80, no special formula. So if it is not arithmetic or geometric, I am not going to make it be very many terms, okay, if that were to come up on a quiz. I'm not going to give you one that's 100 terms and it's not arithmetic or geometric, okay? And so our last one here is, you probably might guess, we saw arithmetic, we saw neither. So this one, if you look, that's exponential, right? So since it's exponential, this is going to be, whoa, holy cow, a geometric series, okay? So if I plug in 0, right, 10 to the 0 is 1, added to 10 to the first is 10, added to 10 to the second is 100, added to 10 to the third is 1,000, added to 10 to the fourth, 10,000, added to 10 to the fifth, 100,000, right? So I can add all those up and get my answer. Now here's the thing. There is a fast way to do geometric, and that's actually what we'll work on later this week. So thankfully for geometric, there's also a quick formula. We just didn't learn it yet, right? So this is just going to be 1, 1, 1, 1, 1, 1, right? So whoop, there we go. All right, so that is it for today. Give those problems a try today on arithmetic series, and let me know if you have any questions.